welcome. Before I talked actually a little bit, as we were going through the population growth examples before, about the fact that expecting that a population is going to grow proportionally to its current population for any amount of time is not very realistic because, eventually either there are limiting factors, resources, food, these kinds of things, and if it's like a disease, you're going to have, you only have so many people who can catch it, and then you have more and more people who become immune to it, and things like this. So what ends up happening is that you kind of have a capacity or an equilibrium state that you eventually will approach and maybe reach. And so this is kind of, this is what we're going to talk about in this lecture, is that much more realistic circumstance. It's just a little bit more complicated. Okay, so we saw before this. So we saw before So let's look at the situation. So for when we have that t equals time, right, and p of t is going to equal the population, right? If we're in this kind of circumstance, right, we assumed this differential equation where I had, so dp dt is going to equal, it's better to use green for functions because it's a little bit more distinct from what I'm using for the other writing. So let's really quickly switch ourselves over to green. So that's dp dt, okay? So this was equal to, and we had some kind of proportionality constant, which gave our growth rate. So this was k times whatever the growth was at that particular, or the population was at that particular time, right? And this was with k greater than 0, or we would have been looking at a decay situation, right? So we assume this situation, right? And then the population grew exponentially. Okay. So what did that look like? What that looked like was having P of t equals, so we had P of t was going to equal, so we had some kind of P naught, or some initial population, and then we took E, and then we had this K for this growth rate, and we had T. Okay? But the population can't grow forever. Right? As I mentioned before, you have limited resources, whether that's humans who are not yet immune to a disease, or whether it's, food or water or whatever the situation is. Population usually can't grow forever, okay? And it levels off as it approaches something called the carrying capacity. So it levels off as approaches the carrying capacity. So as approaches, what's going to be, so this will be blue. And then we talk about the carrying capacity is blue here. So carrying capacity, which we're going to denote by M. Okay. So what's new here. So now that we're kind of aware of this situation, what do we do to deal with it? So new, which is going to be population with, so the differential equation for population with carrying capacity. With carrying capacity. Okay, so this is going to be, we're going to take dp dt so dp dt is going to equal, and then we've got k times p times, and then we have 1 minus p over m. So 1 minus this p over m. Okay. Now let's kind of look at a few observations of what happens if this is a new circumstance. We're going to want some observations of what's going to happen with this. So observations. This is a big important equation. Let's kind of make sure to box that. So observations. 1 is that if p is small, so if this population is small, so if p is small relative to our carrying capacity, so relative to m, relative to m, okay, then that's going to tell us that p over m is small, so p over m is also going to be small, right? Well, looking at our equation, if p over m is small, then this is going to be very close to kp, okay? So dp dt is going to be approximately, so dp dt is going to be approximately kpm, so we're very close to proportional, to the population being proportional to the rate of change being proportional to the population, okay? So the growth starts out exponentially, which is kind of, it's just what I was saying before, right? This early on is a good approximation, but over time it's not, and we want something with a carrying capacity usually. So growth starts out exponentially. Okay. Now, so when we have, if we have p of t equals 0, okay, so that's a solution to this differential equation, right? If I put in 0 here, I get that this is 0. But then the derivative of the constant function 0 is 0. So both sides would be 0, so that's one. So is actually p of t equals m. That one's slightly more tricky to see. So also if we get out our carrying capacity here, as this is a constant function, right? So if we're at the population, the population of m, okay, so then we have an m here, so we have kp, and then we have 1 minus m over m, so that's 1 minus 1, so this becomes 0. But so that tells me that I stop growing at that point. So these are our solutions, right? And then this is also like a constant function, so it would work. So these are solutions. But in fact, they're equilibrium values. Like I was just kind of saying, you're actually getting dp equals 0 at these two solutions, okay? So in fact, they are equilibrium values. Let's write this in blue too. So these are equilibrium values. Okay, so if P starts at 0 or M, so what do you mean by that? We say that if P starts, right, at 0 or at M, so at 0 or at this other equilibrium value at M, well, it never changes from there, right? Then P never changes from that value. Okay, so let's talk about what we have going on here a little bit. We have a different situation, right? We've talked about this before, that population, initially it looks exponential, but as time goes on, there's some kind of capacity, right? I've said this kind of multiple times, whether this is, resources in some sense like food, or resources in some sense like the number of people to catch a disease or something like this. There's a capacity. So it's going to stop growing exponentially after some point. And so we need to worry about the equation that has a capacity. And this is the differential equation that you'll get. Okay. And initially it does start out like it's growing exponentially, but it's going to approach the equilibrium value. So if you started out with no population, that would actually be a solution, right? We get 0 on both sides. It's a solution. But on the other hand, you never would grow anywhere. You'd never have any population. At the same time, actually, interestingly enough, is that you're having your equilibrium value is actually, if I start there, I'm never going to move from there. It's a solution. It is satisfy this, but then you don't move from there. So you will actually keep that that population once you hit that. Okay, so we finally got to talking about what's like a little bit more realistic for what usually happens, and I hope it made some sense. And I'll see you in the next lecture where I'll actually go through how to solve this differential equation and get a solution. So I'll see you then.